totally and explain how superconductor.
That's a good point. I'll do that, I promise. And I'll use the blackboard. So, as you'll see, I got a bit sick of God knows what. So, anyway, so today I will go to the third part of the lecture. And unlike the other two lectures, I will talk about normal state properties. Why I'm talking about normal state? Well, I try to show to you that superconductivity is in close proximity to magnetism. And therefore, if you want to understand superconductivity, it would be great to understand first what is the normal state from which superconductivity emerges. And so I will discuss the magnetic state, and I will show you that there is something very interesting there that is absent in some other materials, which is called the nematic state. Okay. And if I have time, I will discuss about how all these phases compete with each other. If I don't, well, you come next year and I will give a lecture about this, okay? So, as I told you again, you're probably sick of seeing this phase diagram, but we have superconductivity appearing when you suppress spinous wave and orthorhombicity, okay? So, how can I describe this magnetically ordered state? Well, one of the main discussions in this field is whether we should start with an itinerant or localized picture. It's my belief that the truth is in between, but working in the regime in between is very difficult. So usually one either goes to one extreme or the other, and try then to be either increase correlations or decrease correlations. So let me, this is the magnetic ground state, spins pointing out, pointing parallel to each other across the vertical direction or across the horizontal direction. So how many of you here have heard of this term, the itinerant or localized magnitude? Good, so not much of you. So it's not many of you. So what I will do here, I will actually discuss first what is itinerant, what is localized. And you see that there is some gray area there because most systems are not in the extreme limits. So that's what I will do first. Just discuss what is localized and what is itinerant magnitude. So let me do something that we all have seen one day in our lives, the Hubbard model. Okay? So I have two terms. The hopping term, which gives the probability of electron hopping from side I to side J. So you destroy the electron side J, create in side I, vice versa. And this here, by doing that, it gains an energy T. Do you know why the electron gains energy by hopping? Have you ever thought about it? Why does the electron gain energy by hopping? I mean, if I didn't have any Coulomb interaction, why the electron gains energy? Why it wants to hop?
More symmetric wave function.
Huh?
More symmetric wave function.
Well, I would go in an even simpler way of thinking. I would say that it's just a Heisenberg uncertainty principle. By delocalizing it, you increase delta x, okay, and then you decrease delta p. You decrease the amount of energy that you have to pay. Now, okay, so the electron hops. Now there's another term here that is the Coulomb repulsion. And well, as Pierce said yesterday, one of the problems is how to take care of the long-range Coulomb repulsion. In the Hubbard model, this Coulomb repulsion is just intrasite, so only electrons at side I feel the Coulomb repulsion, and only if you have two electrons at the side, they repel each other. So what happens? If you go to the limit where U is much larger than T, this term dominates, and the electrons don't want to go anywhere. The electrons want to be on their side, because if they move to another side, they have to pay energy U. So they wouldn't go anywhere. They form an insulator. That's the so-called Mott insulator. Okay? And of course, that if you were in the other limit where U is 0, this would be a half-field system, which means that it would be a metal. Okay? Now, that's not the whole story. What happens? So this is only in the charge channel. Okay? But what happens if I allow virtual hopping? Meaning that, as you can see, suppose that this electron is here, okay, this guy. Now it hops to this other side and comes back, okay? And then it flips the spins, as you can see. This process actually gives an energy gain for the electrons, and for this reason, it induces an antiferromagnetic Heisenberg model, okay? It induces a coupling between the electrons that want them to be anti-parallel, okay? Again, the reason why they want to be anti-parallel is because only the situation this electron can virtually hop and come back. If they were parallel, by Pauli's principle, this electron cannot hop and stay on the other side. So even in the very strong limit, strong coupling limit, that's what we call, where the Coulomb repulsion dominates, there is an interaction induced by the Coulomb repulsion in the spin channel. And then you form a Heisenberg Hamiltonian, which goes back to the models that Premi was telling to you about, where you just have a J and just the scalar product of the neighbor, that's the nearest neighbor spins. Okay? So as you can see, this J is T squared over U, which in my first assumption, where T is much smaller than U, this is a very small perturbation term. Okay? So as you can see, in this model, the energy gain comes from the kinetic term. Okay? Because it comes from the T squared here. So this is the localized limit, where the electrons are localized in the sites, and the spin-spin interaction is a result of strong Coulomb repulsion and a way of gaining some of the kinetic energy that is here, right? Okay? Questions? Yes? Just let me just see if I can give you the microphone. Tá ligado?
I don't know if I understand. That means that if the gain is in kinetic energy, that means that in the superconducting state, the kinetic energy will reduce.
There's no superconductivity here. Okay? It's just I'm just talking about the normal state. Okay? I will not this lecture I will not mention too much superconductivity, but so here it's just really magnetism. I just want to know where the magnetic interactions come from. Okay? No problem, no problem. Can you pass the microphone?
So, the Heisenberg Hamiltonian here.
Yes.
Is this derived from Hamiltonian?
Correct. Yeah. So what you do here, I mean, I'm not doing all these steps, but you can look at the book, for example, Fazekas or Franklin's book. What you do is you start with this model. Right? You assume U is very large. You construct your Hilbert space. And now you consider this term as being your perturbation and the second order perturbation theory. And then you find out that you go exactly at half filling. Okay, go exactly to this Hamiltonian. Okay? Where this J is just T squared over U. If you want to go beyond half filling, this is called TJ model, which is a bit tricky to solve because you need to guarantee that you always have this constraint of no double occupancy. This constraint can be understood as a gauge field, that there's a lot of things there, but I'm not going to talk about it, okay?
Is ferromagnetism, for example, like say iron 3 oxygen 4, anything related to Hubbard model?
Which material are you talking about?
Iron 3 or oxygen 4.
I unfortunately am not familiar with this material. You can have ferromagnetism due to strong coupling physics, but that involves usually multi-orbital systems. What usually happens in strong coupling ferromagnetism is that you want the spins to be parallel because they're in different orbitals. Okay, here's a single orbital, then it's usually anti-ferromagnetism. You can still find ferromagnetism here. But Stoner is something different. That's what I'm going to talk now. But even in this Hubbard model, you can do a mean field calculation. You actually find some ferromagnetism, but I prefer not going there. Because this is just a digression. There will be a digression and a digression. So I don't want to go there. Okay. Now, so this is one model of localized spins. And localized, again, the spins is an insulator where the spins are fixed. and then because of the Coulomb interplay between Coulomb repulsion and kinetic term, you gain energy in the spin channel. Let me go to the complete opposite limit, the itinerant limit. As the name says, now the electrons are not localized in the sites, but their wave function is just block wave functions. So they are actually, it's much simpler in the sense that it's just free electron gas. Okay? I'm going to claim that unlike the Coulomb term, the localized limit where the energy gain comes from the kinetic term, here, the energy gain comes from the Coulomb term, which is small. It's the other limit of the same model, if you wish. Okay, so how do you understand Stoner model? So let's just remember free electron gas. What is the ground state of a free electron gas? Huh?
Metal.
Sure, but how I describe this metal? What is the main property of the free electron gas? This is a Fermi surface, right? In this case here, that's the Fermi level here, right? I just start putting spin up, spin down, occupying every state until I put all these states there. That's the ground state. Why I'm insisting that's the ground state? Because it's the minimum of energy. Whatever else I do, I'm going to have to pay energy. Of course, that if I artificially separate spin up and down, both of them have to have the same chemical potential. You cannot have more spins up than down. That's not the ground state, right? Very good. What if I want to have more spins up than down? What if I force it by hand to make the subband of spins up more? So instead of having spin up and down equal, I want more spins up than down. What I need to do is start bringing electrons to the excited states. So I pass the Fermi level, right? Now this is not a ground state anymore. We know that. How much energy I have to pay to create such a state? Well, that's probably, it is actually this, but as you can imagine, this is just proportional to this Fermi energy, which is inversely proportional to the density of states that I have near the Fermi level, and that I'm distorting. Okay? So that's energy I have to pay. So how can the free electron gas develop spontaneous magnetization? Well, one thing that I didn't tell you is that there's always Coulomb repulsion. So now Coulomb repulsion is small in this limit. And if I polarize electrons, I gain energy. I gain Coulomb energy, if you wish. Or I have to pay less Coulomb energy. Why is that? Why? Why if I polarize my electron gas, I have to pay...
Pauli inclusion, they cannot be in the same...
Correct, that's exactly Pauli exclusion, right? If every spin is up, they cannot be on the same side. It's the opposite of what I said earlier, right? If they cannot be on the same side, they will be avoiding each other. They don't have to pay the Coulomb term. So at the same time that I lose energy, kinetic energy, I gain Coulomb energy. Okay? Of course, the free electron gas is zero, so this never happens. But if I turn on a small interaction, I can start gaining interaction, and what do you think is going to happen? Well, eventually, the gain energy, the gain Coulomb energy, surpasses the loss in kinetic energy, and then I can actually polarize the term. This will happen when this U, that is the Coulomb Hubbard U, or the local Coulomb repulsion, times density of states is equals to 1. That's called the Stoner criterion, and that's the criterion for ferromagnetism in a metal. Okay? You still have a metal, still have a Fermi surface, but now you have more spins up than spins down. And again, this only is possible because you have a Coulomb repulsion. This is the weak coupling limit, or the itinerant limit of the same model that I discussed earlier, or similar model that I discussed earlier. Okay? But now, again, all the electrons are block wave functions, and you polarize them. Okay? Now, of course, that you say, well, but here's ferromagnetism. How do I get anti-ferromagnetism? I'll go there very soon. But there's another more formal way of showing this thing here. You can start with the Hubbard model in the limit of very small Coulomb repulsion, and then just calculate the susceptibility. What is the susceptibility of the free electron gas? If I have a metal, what's the susceptibility? No. Pauli, thank you. He is for, again, this is for just the paramagnetic localized speed. This is a metal. Okay? So okay, I'm sorry. You said Pauli first and you lost. So it's Pauli, it's a constant, right? Now, if you just go ahead and, this is for the free electron gas. Now we do perturbation theory in the other limit. You start with this term dominating, and include a small Coulomb repulsion. Then you find that this is the susceptibility. Okay, it's the Pauli divided by 1 minus 0. And you know that when this guy diverges, you have a ferromagnet. Divergent susceptibility is a ferromagnet. And again, when this guy is equals to 1, that's the Coulomb criterion, that's when you find ferromagnet. Now, when we expect this to happen, well, it helps if you have a large density of states. This happens when you have nearly flat bands, and this usually is very common in systems that are close to something called Van Hove singularity. A Van Hove singularity, this density of states diverges. So then even a small u would cause ferromagnetism. Okay. Now, what happens if I want to find antiferromagnetism? Well, you do the same calculation, but now not at the ordering vector 0, but at ordering vector q, arbitrary. And that is the general formula for the susceptibility. Okay? But now, notice that I don't have the u at the site, but the u at the wave vector q. Now, there's a very interesting case, that's the so-called nesting case. We say that a Fermi surface is nested if the energy, if the band dispersion with momentum q, k displaced by the order vector q, is minus what you had earlier. Geometrically, it's very easy what I mean. Let's see if I find the special chalk. So what I mean is the following. That's a good idea. What is a nested Fermi surface? Well, what I mean is that, suppose, for example, that I have, this is the square lattice Brillouin zone. You solve the Hubbard model with u equals 0. It's just a hopping term. And you solve that for hot filling. You find that your Fermi surface is just a square. This is the Fermi surface. Okay? Now, if you get this guy here, energy at momentum k, and you want to compare with the energy at momentum k plus q, and my q here is pi pi, you find that one is minus the other, meaning that these parts of the Fermi surface are parallel. This is what's called nesting. That's where the name nesting comes from, I assume. Okay? And that's a very special condition. But when you find this special condition, you find out if you go ahead and calculate the free electron gas susceptibilities, just this expression here, you just use this formula, go ahead and substitute here, you find an equation that is exactly the same as you saw earlier. It's a BCF equation. Okay? Meaning that this is the expression, if I go to t equals 0, the susceptibility diverges. Okay? There's a log divergence here. Now, if I go back and replace it here, I find an expression for the magnetic when the susceptibility diverges. And you'll find again something very, very similar to BCS. Okay? So this is the case of when you have nested bands, the non-interactive susceptibility will diverge at t equals 0. If you include a small interaction, it diverges at finite temperature. Okay? And this is just another way of finding itinerant magnetism in itinerant systems. Any questions?
What if we have a nested and nearly flat band?
Say it again.
What if we have a nested but nearly flat
That's
bands?
actually exactly what happens here. These points here are also Van Hove singularities. That's what's called a Lifshitz transition if you shift your chemical potential.
And when do we know like which instability, ferromagnetism or antiferromagnetism happens?
You need to calculate both susceptibilities and see which one wins at a certain temperature. Okay? But that happens exactly in this model that I told you here. I know that Musso worked a lot with these Lifshitz transitions into a whole singularity train. So maybe he can tell us more about it later. But again, these two cases here that I told you describe what we understand as itinerant magnetism or localized magnetism. And as you can see, it's just a difference in which term is the dominant one. For localized, the itinerant term is the Coulomb repulsion, tends to form an insulator. For itinerant, the weakening term is the hopping one, is the kinetic term, forms a metal. Okay? Now, which one of the two do you think? Let's take a very simple material. Tell me a material that you know is magnetic. A simple one. You still have lots of meat in there, huh? Which material is a magnet that you learned when you were like 3 years old? Iron. Thank you very much. Do you think iron is itinerant or localized magnetism? Why? It's a metal. Now, do you think this little theory that I gave to you describes iron? You didn't seem to make a pretty face, right? Well, actually, it doesn't, because even though it's a metal, I mean, you can understand as a starting point, but the main issue there is that this U is not that small that you can do perturbation theory, but not that big that localize the system. That's the intermediary regime. It's hard to treat, okay? Anyway, so keep that in mind, because now I'll go back to the pnictides. Now we can discuss about the itinerant localized magnetism here. So, as I told you, there's several systems that are in this intermediate coupling regime, and nickel is another one, very known. Now, the issue is that the magnetism in the pnictides are metals. They're not particularly good metals, which also suggests that Coulomb repulsion is important. Okay? But they're still metals. So there are two different points of view. You can start at strong coupling or weak coupling. I will show you the weak coupling perspective, where we start considering the system as metals and just see what terminal Coulomb repulsion causes. Okay? Now, we can skip this part. So, how do I understand metal? Well, I need to go and look at the Fermi surface. So if I look at the Fermi surface, that one that I draw to you over there, I have hole pockets in the center of the Brillouin zone and electron pockets displaced by pi 0, 0, pi. So it's very evident from here that if I take this band, the blue one, just invert it because I want a minus sign, and shift it by pi 0, I will get something very similar. Okay? So nesting is there, and Honjin told you about that. Whether nesting is enough or not is a different story, but you can see here from ARPAS that this picture is not that crazy, right? We start increasing the doping, the nesting becomes worse, and not surprisingly, when nesting goes away, you don't find magnetism anymore. Now, this is not perfect nesting in the sense that if I take this band and displace by pi 0, it doesn't go exactly on the top of the other band. It's different than the case that I drew on the board here, where if I displace by pi, it goes exactly on top of it. Okay? So that log that I told you, it's actually going to be cut off. So weak coupling is really not the right word, because you need some interaction threshold to find magnetism. But what you find is that there is some nesting features in this observed experimentally. And then if you include some small interaction, you're going to cause instabilities. Very good. What is the problem here? Or what is the issue? Why is this different than what I was telling you earlier? As the answer. Because I have two simultaneous instabilities. It's not only pi 0, but it's also 0 pi. And this is guaranteed by symmetry, because this has tetragonal symmetry. So this band has to be exactly the same as this one rotated by 90 degrees. So, if I have this instability, I can also have this one. If I write the most general spin operator in terms of these two instabilities, it is a linear combination of these two. But in the pnictides, as I told you earlier, you find either pi is zero order or 0 pi, never a combination of them. How do you understand that? Well, to answer this question, we need to calculate the energy. What is the free energy of these states, and show that the one that minimizes the energy is the one where either M1 is 0 or M2 is 0, but not that both of them are non-zero at the same time. How do you do that? Well, there is this procedure, or this is approach called Hertz-Millis, where you start with your microscopic Hamiltonian, integrate out your electrons, and derive your free energy in terms of M1 and M2. Okay? This is explained in all the following slides, which I will skip. It's on the Dropbox, you can follow it. I'll just tell you what it is. You introduce electrons on 3 bands, okay? You introduce all the possible interactions. There are 8 possible interactions. This is equivalent to a multi-orbital Hubbard model. Then you integrate out, so then you project the interactions in the spin channel. Then you integrate out, introduce the magnetic order parameters via something called Hubbard-Satanovich. Then you integrate out your electrons, and then from there you calculate, you can obtain your partition function from where you derive your free energy. I'm not going into these details. It's on the notes, and on its own, it's quite something that requires some work, but you can do that if you wish. And I'll be happy to answer questions, technical questions, but that's not what I want to do. Just tell you how to do this procedure, okay? And then you expand for a small m, and you obtain a Ginzburg-Landau model. Okay, so again, this is derived. All these coefficients depend on the band structure on the Green's functions. Okay? And now we can study that and see what our model gives. So, well, weird theories, Pascal said, we have lots of prerogatives that experimentalists don't, such as putting parameters to whatever value you find more interesting. So the first idea is to, well, you know what, dealing with elliptical bands is a bit complicated. Let me consider everybody to be circles, such that I have perfect nesting. What perfect nesting means? That these circles are exactly the same. Then I go back and look at my free energy. That's the form of my free energy. Okay, and these coefficients depend on the Green's functions, if you ever want to know. You don't need to. And what you find out if you work out these coefficients is that this A is temperature minus the magnetic transition temperature, and U is positive. So A is positive above the magnetic transition, negative below. And actually, that's what you get, because if you do just mean field solution, meaning that you minimize this free energy with respect to M1 and M2, you find that the solution, the minimum, is when M1 squared plus M2 squared is minus A over U. Now this is positive. This has to be positive to have a solution. It means that A has to be negative, which means that T has to be smaller than Tm. So A equals 0 is the onset of long-range magnetic order. Who here has seen some sort of Ginzburg-Landau theory like this one that I'm drawing here? Okay. Oh, thanks, Pierce. I was worried that you might not have seen that. Any questions about this?
Why do you choose to make that finite temperatures and not equal 0 since you are looking for the box state?
That's a good question. I mean, what I'm interested now is in the parent compound, where the transition is at finite temperatures. So if it equals 0, I can. The only difference now is that this guy here, I have to consider the dynamics, right? And but that doesn't change much. Now it's not going to be a function of temperature, but it's going to be a function of some parameter that brings my transition, to 0. So in this case here, it would be going away from perfect nesting. But this is fully quantum mechanical, right? In the sense that here I'm summing over both momentum and Matsubara frequency. So it's just a question of whether the transition is at finite temperatures or at 0 temperature. Okay? And again, the expansion only works near the transition temperature. So very good. Now comes the first problem. You see that ground state is whenever m1 squared plus m2 squared is constant. This means that I can mix anything that I want. I can have m1 is 0 and m2 non-zero, which is this striped state. m1 non-zero and m2 0, this is this other striped state. That's what experimentally see in the pnictides. But I can combine both of them to be perpendicular. Then I get this state. Or I can combine them to be parallel and I get this state. These states are never observed. So my model is not capturing the whole physics here. Where do you think I'm screwing up? Yeah, that's the first candidate, right? Why I'm doing perfect nesting, right? This is not perfect nesting. Okay, so I'll follow your suggestion and do very quickly here away from perfect nesting. Okay, and then you'll find a new term appear in your free energy, which actually makes a distinction between M1 and M2. This G here, it doesn't matter what is the value, all you need to know is that this is positive. Why it's important? Suppose that I minimize this energy, you don't need to do any calculation. This term here does not differentiate between M1 and M2, so you can forget about it. Now this term here, the only terms that couples M1 and M2 is the cross term, which is plus, there are two minus here, gm1 squared m2 squared. This is energy. What happens if I have both non-zero? I pay energy. If I make one of them 0, I don't pay energy. So the ground state, you'll find out, is either m1 0 and m2 non-zero or vice versa. Now I got the right ground states. So in the itinerant model in the pnictides, the right ground state only appears because of the band structure not being C4 symmetric, but being tetragonal at the borders of the Dulon zone, which is natural to expect. Okay? Now this G may change sign. If G was negative, then you want both as big as possible and non-zero. Okay? Then actually you get this state here. There are some reports that this state has been spotted in the pnictides, but I'm not going to go there. It's still it's very recent. It's very, it was presented in this last March meeting, but we're still not sure what to do so far. Well, question. He's delaying the joke. Who has the microphone? Oh, can Mus is going to press the microphone here. Thank you. You go back.
How does it select then between the M1 equals 0 or M2 equals 0? Does that have to do with uniformity?
That's exactly the next part of my talk. Very important question. Thank you. I give you the $50 later.
Okay.
See, your former student just stole my
I have a question about the nesting. So in principle, if you have both Fermi surfaces pretty much the same, it's obvious that you can shift one on the top of the other and have perfect nesting, great. But if they're not exactly the same, it looks like there is a range of k that you can shift that. So you would have a range, like a delta key at which you would see some instability. So how do you formally deal with that? Because not just for a particular Q, and how is that important?
Well, that's a good question. I did not go into these details here, but what happens, what you're describing is what's called incommensurability. Meaning that your order vector is not going to be exactly by 0, but a little bit shifted. Okay? This general model predicts some incommensurability, but only at higher dopings. And actually, there are, in cobalt dope, the nickel dope, the neutron scattering sees incommensurability. Okay? Who does neutron scattering here? You were an author of that paper. Both of them. You saw that too. Here you go. Yeah. So that's a very important point, and that's causing incommensurability. Yeah. What is surprising is why so few dopings are incommensurate. And that is a challenge for this model. I think Musu had a question.
This term doesn't change the order of the phase transition, or it's still...
Very good. Can I delay your question to the next session? It will. It might change. Because it's going to give rise to an emergent degree of freedom. But it might. Okay, so now, I was not in a band when I was in the 70s. So yesterday you guys went to the Christ, right? And we went to the cross, meaning that we were working here. And we realized that, there's some real-life example of system frustrated interactions. And that's going to set an example for a premise lecture in the end of the day. She's going to talk about frustration. And then put frustrating interaction. So we just here enact what usually happens, or what sometimes happens in panel discussions or conferences, right? So whoever guesses where I took this from gets a free drink tonight. You guys are too young. Pasquale, where do you know? Pasquale knows because he was next to me. Go ahead.
Isn't that an album cover?
No, that's Monty Python.
Oh, Monty Python.
Holy Grail. You should have. So, that's what usually happens, right? You have a full auditorium, completely full, people very interested, and they have a question. And we, the panelists, get very interested about the question. And we are paying lots of attention to it, right? Now, the frustration happens here. We have different opinions, but we are all very civilized, and we only respectfully disagree with each other. We never get upset. And yeah, you can get autograph of the actors later. But of course, because we all come to the same page, also very rationally. And that's where frustration comes, because then, when they go back to the audience, they fell asleep. So, anyway, because it was not in a band, we had to make this little theater. So we were hardly working yesterday afternoon while you guys were enjoying it. Okay? Very good. Now let me go to the second half of my talk. Any questions about the enactment? Okay. Any questions about magnetism? Huh? Well, the producer was Pasquale, producer. He has the cover of his band in the same seal, Any questions? Now I'll talk about pneumaticity, and that's going to connect to the questions that both Travis and Musso asked, which is that this new term gives rise to new physics. Why we talk about pneumatics? There's nothing, I showed the phase diagram. Was there any pneumatics there? No, there wasn't. Why talk about it? Well, this idea appeared and is now very solid, because if you look at this phase diagram, there's something that is not particularly, that is very actually, you just look at it here, and you find that the orthorhombic transition line always follows the magnetic one. And this is taken for real data, and if you don't believe me, you can ask Greg. He didn't take these data, but you were in the group when we were writing this paper, so you know that this is true. So including this backbending here. Now these phases have to be correlated. They cannot just be two independent phases. Okay? Now, what this very smart experimentalist did, it was Ian Fisher in Stanford and Macquarie Janitor in Ames. They found a way of looking at the isotropies of this orthorhombic phase. Why do I say that they found a smart way? What happens in a big sample? You guys are, many of you are experimentalists. What happens if I have a big sample? Why do I not see any orthorhombic or any isotropic property? Twinning. You guys work on that. You're not fair. What happens is that you're going to have some domains where the x-axis is larger than the y-axis, and some other domains where the opposite happens. Right? This is what's called twinning, if you wish. And if you try to measure, for example, resistivity along A or B, it's going to be zero, the difference, because you have equal domain population. And that's a problem. Now, what they developed was a way of detwinning the samples, which is a very smart way, but I'm not going to discuss the experimental details. But this allowed us to look at the resistivity and isotropy, for example. You measure resistivity along A and B, and you see they are very different. Now, can we understand this resistivity and isotropy only because of the lattice distortion? The answer is no, we cannot. If you look at its size, this is a color plot. Why this resistivity and isotropy is 100%, more than 100%. Now the largest orthonomic distortion is here, doesn't match the maximum resistivity, it's smaller than 1%. So then